Hi, welcome back to educator.com. Today we're going to have an introduction to logarithms. At this point, if we want to find the value of a number raised to an exponent, it's easy. We use our exponentiation rules and evaluate. If it's something simple like 2 cubed, then we know that's 2 times 2 times 2. 2 times itself 3 times, which we figure out is 8. And we also figured out how to do numbers that weren't just simple integer exponents, but we've got all these nice rules from our previous few lessons. But what if the question was inverted? And what if we knew the base and the end result, but we don't know the exponent that we need to get there? If we knew that we had 2 as the base, and we wanted to have an end result of 8, but we had no idea what exponent we had to use to get to 8. How could we figure out that exponent? This is the question that leads us to explore the idea of the logarithm, which we'll be looking at over the next few lessons. We define the logarithm as a way to talk about this unknown exponent. The logarithm base 2 of x, denoted log 2x, with this little 2 as a subscript right here, so log base 2 of x, is defined to be the number y such that 2 to the y equals x. So when we see log sub 2 of x equals y, then we know that that would be 2 to the y equals x. So in other words, we're looking for the number that when the logarithm goes onto some number, we're trying to figure out what value, if it raised to this base here, would become the number that we took the logarithm of. So for the example of log 2 of 8 equals 3, the reason why that's the case is because we're looking for what number here do we have to raise to get 8. So the answer there is 3. If we raise 2 cubed, we get 8. So we know that log base 2 of 8 equals 3. It can be a little bit confusing to remember how this works at first, what the notation means. So when you see log base 2 x equals y, you can think of this as if the 2 were under the y. If we had 2 to the y, it would make the x that we're taking the logarithm of. So we take the logarithm of some number in regards to some base, and that tells us what number we would raise the base to get the original number we're taking the logarithm of. It'll make more sense as we see more examples. Here's some other examples. So log base 2 of 32 equals 5, because if we raise 2 to the 5th, we get 32, right? 2 times 2 times 2 times 2 times 2 is equal to 32. 4, 8, 16, 32. Log base 2 of 1 equals 0 because if we raise 2 to the 0, from our rules about exponents, we know that's just the same thing as 1. Log base 2 of 1/4 equals -2 because we know if we raise 2 to the -2, then that's the same thing as 1/2 raised to the 2, right? We flip to the reciprocal, and 1/2 squared would become 1/4. Which is what we initially started with. So it's a logarithm is a way of taking a logarithm of a number so that you figure out what you would have to raise some base to get the thing you took a logarithm of. We can expand this idea to something beyond just base 2, to a general idea. The logarithm base a of x, log base a x, so that little a right here down here is a subscript, where a is greater than 0, and a is not equal to 1. So our base has to be greater than 0, and our base has to not be equal to 1, is defined to be the number y such that a to the y equals x. So if we take log a x, then we know that that gives us some y, and that a to the y equals x. So once again, it's the same idea where if we take this base and we put it under the y, we would get a to the y, and then we would have the thing that we were originally taking the logarithm of is what we've got there, right? That's what's occurring right here. So the idea of the logarithm is you take the log, and it tells you something that you can raise as a number to be able to get this other value. It's a little bit complex the first time you get it, but as you do it more and more, it'll start to make more sense, and we're going to see a whole bunch of examples to really get this cleared out. Now, notice we've got these restrictions on what our base can be. We know that the base has to be greater than 0 and the base is not equal to 1. The base a of a logarithm has the same restrictions as the base of an exponential function. This is because exponential functions, exponentiation, and logarithms, they're inverse processes. They do the opposite thing. And we'll see more about how they're inverses in the future, but they do reverse things, so they've got to have the same restrictions because they're basically working with the same idea of a base. They're being seen through different lenses, and it will make more sense as we work on it more and more, but we've got to have the same restrictions on it. Otherwise, the idea of a logarithm just kind of not make sense or not be very interesting. So we've got these restrictions that we have to have our base greater than 0, and we have to have our base not equal to 1. Let's look at some examples to help clear this idea up. So log base 7 of 49 equals 2, because if we move this base over, then 7 squared is just 7 times 7, which gets us 49, which is exactly what we started with. So this is the case because 7 squared equals 49. Or let's write it in the way we had it originally here. 49 equals moving the base over, moving our base underneath the right side, we have 7 squared like this. Same thing over here. We know log base 10 of 10,000 equals 4 because if we move our base under, we know that 10 to the 4th is equal to 10,000. The question being, if we want to know what number do we have to raise 10 to get 10,000. That's what log base 10 of 10,000 is effectively asking. It's saying what number do we have to raise 10 to, raise our base to get 10,000 as the end result. 10 to the what equals 10,000, and the answer to that is 4. So if we take 10 to the 4th, we get 10,000, and sure enough, we see that that is 10 times 10, 100 times 10, 1,000 times 10, 10,000. Same thing going on over here. If we have log base 5 of 1 over 125, then we move that under and we get 5 to the negative 3 is equal to 1 over 125. Let's check that out. 5 to the negative 3. 5 to the negative 3 is the same thing as 1/5 to the positive 3, right? We flip to the reciprocal, and then 5 times 5 times 5, 25, 125. So we get 1 over 125. Sure enough, checks out. Finally, if we take log base 4 of 2, then we see that 4 to the 1/2 is equal to 2. What is 1/2? 1/2 as an exponent means square root. 4 to the 1/2 is the same thing as the square root of 4, which is 2. So once again, that checks out. So it's the question of what exponent am I looking for to be able to get this base to become the number that I'm taking a logarithm of. We can even do this with more unusual bases on our logarithms. For example, if we have log 1/2 of 1 over 16, then we can see that that will become 4 because 1/2 to the 4th is equal to 1/16, right? Because 2, 4, 8, 16. So 1 over 2, 1 over 4, 1 over 8, 1 over 16. So we see that that is the same thing. If we take log base pi of pi, then we know that it's got to come out as 1 because pi to the 1, hey, of course, that's no surprise that it's going to equal what it already started with. So if we're taking log base pi of pi, then the thing that pi has to be raised to get pi is just 1. So we have 1 as the thing that comes out of that. If we take log root 2, log base root 2 of 4 times root 2, then we get that that's got to be 5 because root 2 to the 5th, sure enough, that's equal to 4 root 2. We can check that out. Root 2 times root 2 times root 2 times root 2 times root 2. Well, root 2 times root 2 becomes 2. Root 2 times root 2 becomes 2. And we've got this 1 root 2 left. So 2 times 2 is 4. And we're left with 4 root 2. Checks out. Final one, log base e of 1 becomes 0 because if we move this over, e to the 0, just like anything raised to the 0, becomes 1. So it checks out. So we've got some idea of how it works. A logarithm is, for this base, what number do I have to raise it to get the number that I'm originally taking the logarithm of? When I take the log base 10 of 10,000, it's a question of what number do I have to raise 10 to get 10,000? I have to raise 10 to 4 to get 10,000. When I take log base 7 of 49, it's a question of what number do I need to raise 7 to get 49? The answer to that is 2. That's the idea of a logarithm. The two most common logarithmic bases to come up are the numbers e. Remember, e is the natural number. We talked about it previously when we talked about exponential functions. Very important idea. And 10. As such, they have special notation because we have to write them so often. The base of e is expressed as ln. So when we want to talk about base of e, the shorthand for that is ln. It's called the natural logarithm. Remember, e is called the natural base, so when we're taking a log base e, we call it a natural logarithm, and we use ln because originally the French were the ones who came up with this, so it was logarithm naturel. Excuse my French, I'm not very good at speaking French. So natural log of x is equivalent to log base e of x. ln x is just a shorthand way of saying log with a base of the number e. Base 10 is expressed with just log on its own. Notice it has no subscript. There's no little number down there. If no base is given, it's assumed to be base 10. Since base 10 comes up a lot, it's just an easy way to write it. This is normally what it means. It's called the common logarithm because it's a commonly used logarithm. So if you see log base x, notice it has no little subscript, no little number down there, then we know that that's going to mean log base 10 of x. Well, we can find the value of expressions like log base 2 of 8. We know that came out to be 3 because the number that we raised 2 to get 8 is 3. How do we figure out the value of more complicated expressions? Like if we wanted to figure out the natural log of 12.19, and as we just saw, that'd be the same thing as asking what is log base e of 12.19? Well, e is a very complicated number, right? It goes on forever. It's irrational. 12.19, that's not a very friendly looking decimal number. So how are these two things going to interact? We can guess it's probably not going to come out very cleanly in a nice way. Sure enough, it doesn't. Comes out to be approximately 2.500616, and precisely it would keep going forever as well. So for calculating logarithms, just like exponentiation, we can find the expressions, or a very good approximation, by using a calculator. Any scientific or graphing calculator will have natural log and log, base 10, buttons to take logarithms base e and 10 respectively. However, many calculators will not have a way to take logarithms of arbitrary bases. So if we had like log base 3, most calculators won't have an easy way for us to just get what is log base 3 of some number. But there is a way around this, and it's called change of base. So if you do need to take the log base 3 of some number, check out the next lesson, Properties of Logarithms, where we'll explore how can you change from one base to another. So the way that you calculate complicated logarithms like this is you generally just use a calculator. The calculator has a method to be able to figure out what does that come out to be. Now, just like with exponentiation that we talked about before, we should note there are ways to calculate these values by hand. We could do this by hand and figure it out, and you'll learn about this in more advanced math classes, but we won't learn about it in this course right here. Doing this takes a lot of arithmetic, though, and so we designed calculators to speed up the process. It's something that we could do. It's not like we're completely reliant on calculators for figuring this idea out. Logarithms weren't something that we only got once we had calculators created. We've been able to have this idea for a very long time, since the 1600s in fact. But being able to calculate what these numbers come out to be, that takes a long time. It's a slow process, so we've got calculators to be able to figure this out for us very quickly, very easily, so it speeds things up. But it's not that we're dependent on calculators, it's just that they're a useful tool that we can apply in this situation. Graphs of logarithms. So now, since we can evaluate logarithms however we want, because we've got these nice calculators as tools, we can plot graphs of them. So let's look at some graphs. F of x equals log base 2 of x. This is in red. G of x equals log base 5 of x. That one's in blue. And finally, h of x equals log base 10 of x. That one's in green. So notice how short the y-axis is. It only goes from -3 up into +5, but we go all the way out to +100 on the x-axis. So we can see that here, right here, it's hard to see, that is a 1 value on the x-axis, and that's going to correspond to, that's going to wind up corresponding to 0, because log of anything, log of any base of 1 will come out to be 0 because the number that you raise anything to, a to the 0, equals 1. So if we would take log of anything, if we take log base anything of 1, it's going to always come out to be 0 because that's the number that we raise anything to get 1 in the first place. So that's why we see a common height of 0 there. And notice how slowly they grow, right? At 16, log base 2 is only going to be at a meager 4. For log base 10, when we look at log base 10, it takes getting all the way out to 100 to even get to 2, right? If we go out here to the 2, it takes all the way of 100 to be able to get that from log base 10 because 10 to the 2 equals 100. We're seeing a similar thing for log base 5. It has to get all the way up to 25 before it hits this height of 2 as well, because 5 squared. And we aren't even going to see it hit height 3 because it's not going to hit a height of 3 until it manages to get to 125 as an input value, because 5 cubed becomes 125. So notice how slowly these graphs grow. These graphs grow really, really slowly because for logs it takes a really big number to be able to get even slight increases in our verticals. And the farther out they go, the even slower they're going to grow. Now notice that they approach the y-axis asymptotically. So as they get smaller and smaller, they get really, really close to this y-axis right here. They never touch or pass it, although that might be hard to see in this picture since it looks like it's right on top of it. But they get very close. So they won't actually touch it, but they get very close to the y-axis. We'll talk about this behavior of how it gets really close to the y-axis and why it can't actually touch the y-axis or go past it soon when we talk about the domain of a logarithm. The logarithm is the inverse process of exponentiation. For example, let's consider base 2. If we have log base 2 of x equals y, then we can see its flip of 2 to the y equals x, right? We just change the x and the y location. So log base 2 of 8, if we take log base 2 of 8, that becomes 3, because remember, 2 cubed equals 8, so when we take log base 2 of 8, we get 3. But then if we take that 3 and we plug it into the other one, we take the 3 and we plug it in up here, so we look at 2 cubed, hey look, we're right back where we started. We have the same thing on both sides. Sorry, we take this log and we do something to it, and then we do the reverse process with the same base as exponentiation. We get back to the original input that we put in. Same thing, if we did it the other way, where we did exponentiation first, if we take 2 to the negative 2, then that's going to flip to 1/2 squared, so we'd get 1/4. And then if we take log base 2 of 1/4, we're going to get -2. So exponentiation logarithms, they're doing inverses. One goes one way, one goes the other way. Together, they cancel out. We'll be discussing this idea a lot more in the coming lessons. It's a very important thing. We'll also be proving it in general. We can see this as one in its general form for any logarithm. The exponential function of base a is the inverse of the logarithmic function of base a. It is critical, though, they do have to have the same bases. Our exponential function is base a, and our logarithmic function must be base a. If they're not the same base, it won't work. Let's see why this is the case. If we have f of x equals log base a of x, f inverse of x equals a to the x, then we can take f inverse of f of x and see what happens. And remember that we're talking about stuff from our lesson on inverse functions. If you need more background on inverse functions, make sure you go check out that lesson. It'll help you understand what's going on here. So f inverse of f of x equals, well, we could do this as, since this is a to the x, then it's going to be, well, we'll apply f inverse next. First, f of x equals log base a of x. So we've got log a x. Then we apply the f inverse, and we've got a to the log a x. Now, what's that wind up coming out to be? Well, remember, log base a of x equals y is the same thing as saying a to the y. Remember, a to the y equals x. So that's what log ax is. It's this y. It's some y such that if we were to put it as an exponent on a, we'd get x. So log ax equals y. Well, we can just say whatever the number log ax is, let's call it y. So we can swap that out and we can say a to the y. Just because we're saying log ax, we'll call it y. So that's what we have over here. But remember, we defined this idea of what log ax is based on a to the y equals x. Well, we now have a to the y equals x. So if a to the y equals x, then that equals x, which means that f inverse of f of x equals x. Whatever we put in as our input comes out as our output if we do these two functions one on top of the other. We've got inverse functions because one function cancels out the effects of the other function. We'll talk about this more in future lessons. We can also see this in the graphs of exponential and logarithmic functions. So if we take two graphs of, say, 2 to the x, that one's in red, and log base 2 of x, we see them like this. And then finally, we also have y equals x in yellow here coming through the middle. Now, remember from our lesson about inverse functions, when we learned about inverse functions, we know that if two functions are inverses, they mirror over the line y equals x. So they mirror each other over the line y equals x. They're swapping x and y coordinates. This shows us that they have to be inverses. So for example, if we look at what is log base 2 at 2, hey, it comes out to be a height of 1, right? Here's a height of 1. And then if we look at what is our 2 to the x at 1, it is a height of 2. So for this one, we've got 1, I'll color code it back to what it had been. So for this one, we've got 1, 2. But for the blue one, we've got 2, 1. They flip x and y locations, and that's going to be true wherever we go on this because we see that they do this thing with y equals x where they mirror across it. Their x and y locations swap, showing us that they're inverses. Notice all the graphs we've seen of logarithms, they never pass or even touch the y-axis. So they never pass the y-axis, they never even manage to touch the y-axis. This is because the domain of a logarithm is 0 to infinity. And notice there's a parenthesis on that 0, so it says not inclusive. So not including 0, everywhere up from 0, but not including 0, all the way up to positive infinity. We can see this for a couple of reasons. First, since exponentiation and logarithms, they're inverses. That means that the range of an exponential function is the domain of a logarithm. The range of f of x equals a to the x is going to be 0 to infinity, right? A to the x, if we put in any base a that's greater than 0 and not 1, it's going to go anywhere from 0 up into infinity, right? If we look at 2 to the x, by varying what we plug in for x, we're going to be able to get anything between 0 and positive infinity. Now, let's talk briefly about this idea. So if we had sort of a pool of numbers that we called A, the set of things that we're allowed to use, and then we had another pool of numbers that was B, the set of things that it's possible to get to through some function f, right? We've got some function f that takes numbers from A and it goes to B, then we call the numbers over here domain. We talked about this when we first talked about the ideas of functions. So here's the domain of f, and over here is the range of f. So the domain of f is everything that f is able to take in. The range of f is everything that f is able to spit out. So for the example a to the x, or the example 2 to the x as a specific example, the domain is anything, right? It can take in any positive number, it can take in any number at all, negative infinity to positive infinity, any real number whatsoever, but it's only going to be able to spit out numbers from 0 to infinity. So in this case, we see it's going to have its range as 0 to infinity. Now, notice, if we do the reverse of this, if we want to see the reverse of this, a function that does the opposite of what f does, f inverse, then it's going to have to go not from A, it's going to have to go from B. So its domain, the domain of f inverse, is going to be going in the other direction, right? Since it's taking what f did and it's reversing it, it has to be able to take the things that f does as outputs. Whatever f makes as outputs, whatever f spits out, is what if inverse will take in. So the domain of f inverse is the range of f, which means that the range of f inverse is also the domain of our original function f, right? F goes from A to B, f inverse goes from B to A. Now, we saw that for any exponential function, its range is 0 to infinity. So that means that the domain of f inverse, the domain of a logarithmic function, since it's the inverse of exponentiation, must also be from 0 to infinity. So that's why we've got this domain here. The domain of any log has to be from 0 to infinity because the range of any exponential function is from 0 to infinity. So they're going to be done as opposites. The range of an exponential function is the domain of a logarithmic function. So that's sort of a highfalutin way of being able to understand why this has to be the case, because we can say what we learned about inverse functions applies here because we've got an inverse function. But alternatively, we can just see that it would not make sense. It is nonsense if we look at it otherwise. Consider if we try to take log base 2 of 0. Then we know that that's got to be equal to some number b for it to be a possible thing. Then that means that 2 to the b, right, 2 to the b has to somehow be equal to 0. But that doesn't make any sense. No such number b exists, right? No possible number could exist that would be able to take 2 and turn it into 0, right? 2 to the b can't ever become 0. If we plug in any number, we can make very small numbers, but we can't actually get all the way to 0. We can't touch 0. The same is going to go for negative numbers. If we wanted to say 2 to the b equals -4, there's no number that does that, right? We can't raise 2 to some number and make it negative. It started out positive, so we can't possibly make it negative, so this is impossible. This is impossible, this is impossible, so it means that log base 2 of 0 is an impossible idea. We can't take the logarithm of 0 or anything that's going to be negative because it just won't be possible for it to work over here where we're trying to figure out what would be the exponential version of it. So since it just doesn't make sense to take the logarithm of a number that's 0, to take the logarithm of a number that's negative, it must be that the domain is always positive. We have to go from 0, but not including 0, all the way up to positive infinity. We can take in any of those things, but we can't take in 0, we can't take in negative numbers, so that explains why our domain has to be this. We can think about it that way, or we can think about it as this flip idea of the fact that exponentiation and logarithms are inverses, so we can have this more complex idea of the domain and range of what those things has to be, but we can also just go to the fact that it does not make sense. It would be nonsense, and that's a reasonable idea too. All right, ready for some examples. Let's evaluate these numbers without a calculator. So if we're looking at log base 6 of 216, then that's going to be equal to some number such that when we raise 6 to that number, we get 216. So 216 equals 6 to the question mark. We want to figure out what this is. So let's see, what are some numbers that we can get out of this? 6 to the 1, well, that's just 6. 6 squared, well, that would be 36. 6 cubed, 180 plus 36, 216. Hey, bingo, that's what we're looking for. So it must be the case that it is 3. Log 6, 216 equals 3. That's our answer. Excuse me. We've got log, if we've got log of 1 over 10,000, first thing we want to do is remember if we've got just log, then that's a way of saying it's log base 10. So log base 10 of 1 over 10,000. Once again, we're asking, what is that going to be? Well, that's going to be the number such that 10 to whatever that number is going to be equal to 1 over 10,000. So let's look at possible numbers for 10. If we go positive, we have 10 to the 1 equals 10. Well, that's not going to work because we're going to need a fraction. So we notice 10 to the negative 1, well, that's 1/10. And then if we think about that, 10 to the negative 1 would be 1/10. 10 to the negative 2 would be 1 over 100. 10 to the negative 3 would be 1 over 1,000. 10 to the negative 4 would be 1 over 10,000. So 10 to the negative 4 equals 1 over 10,000. We can also see this because we can count the number of zeros. 1, 2, 3, 4. So that's 10 to the 4th. And since it's 1 over 10 to the 4th, then that must be 10 to the negative 4. So we've got negative 4 is what we have to raise 10 to get 1 over 10,000. Natural log of e to the 17, well, natural log, remember, natural log is just another way of saying log base e. So log base e of e to the 17. So what number do we have to raise e to? So e to the question mark is equal to, well, the thing we're working with is e to the 17th. So e to the 17th would be e to the question mark. Well, that's pretty clear. The thing that the question mark has to be is the 17. Otherwise, they'll never match up. So it must be e to the 17 that we want here. So 17 is our answer. Because if we raise e to the 17, it's no surprise we get e to the 17th. Finally, log base 4 of 32. Once again, we're saying what is the number that we have to raise 4 to get 32. So we move that over. We can think of this as 4 to the question mark is equal to 32. So 32 equals 4 to the question mark. Well, let's start looking at some possible numbers for 4. So we could have 4 to the 1. Well, that'd just be 4. Not big enough. 4 squared. Well, that'd be 16. Hey, we're starting to get close. 4 cubed. That would be 64. Oh, dang. Looks like we overshot. Oh, well, we might notice 16 times 2 equals 32. So if we could somehow get 2 to show up, we'd be good. Well, notice 4. How is 4 connected to 2? What's the connection between these numbers? Well, the square root of 4 is equal to 2. Well, we also had another way of saying that. 4 to the 1/2, is that's the same thing as saying square root. So 4 to the 1/2 equals 2. So we see that 4 squared times 4 to the 1/2 equals 32. 4 squared times 4 to the 1/2, because 4 squared is 16. 4 to the 1/2 is 2. 16 times 2 gets us 32. So now we just need to combine those. 4 to the 2 times 4 to the 1/2 is just another way of saying 4 to the 4 over 2 times 4 to the 1/2. We can add them, they're on a common base, so 4 to the 5/2. So the answer for this, the number that we have to raise 4 to get 32, is 5/2. All right. What if we were doing the other direction? If we wanted to write an exponential equation in logarithmic form. So we've got these exponential equations, 3 to the 4th equals 81, and now we want to do it in the logarithm form. Remember, we have log base a of x equals y is the same thing as saying a to the y equals x. Remember, our base here, we can think of it as popping up under what's on the other side of the equation. So this over here is the exponential form. This here is the logarithmic form. So logarithmic form is this log stuff, and exponential is this a to the something stuff. So what we've got is exponential forms here, so we want to flip it. So 3 to the 4th equals 81. Then that's going to be log, what's our base? Our base here, the 3, so log base 3. What is the number that we're raising to? That's the blue, so we're not going to use that. Finally, the number that we've got, x, so log base 3 of 81 is equal to the number that we have to raise to, 4, because 3 to the 4th equals 81. If we ask what number do we have to raise 3 to get 81, that's going to be 4. 3 to the 4th equals 81. We can do this with any of this stuff. So 10 to the 2.4 equals 251.18. Then that's going to be, our base is 10, so we can write that as just log, because if we don't have a base, it just says log base 10. So log of what number? Our number that we're going to get to is 251.18, and it actually keeps going, so we'll leave those dots there to show that it keeps going. And that's going to wind up equaling 2.4, because the number that we have to raise 10 to get 251.18 is 2.4, as was shown to us in our original exponential equation, in our original exponential form. So another one, our base here is e, so we can write that as natural log. Natural log of this number, we were told, comes out to be 4. Finally, our base pi, so log base pi of this number is equal to the square root of 1/2, because we know if we raise pi to the root 1/2, we get 2.2466, and continuing on. So that's how we're able to figure out that log pi of 2.2466, continuing on, must be the square root of 1/2. Graph f of x equals log base 3 of x. So to do this, we want to start off with a nice table to figure out the values. So x, f of x. So notice, you probably don't want to just toss in numbers willy-nilly. If we plug in 10, well, I don't know what number we have to raise 3 to get 10. That's going to be something complicated. We have to use a calculator. But we do know what it's going to be if we plug in numbers like, say, 3, right? If we plug in 3, what number do you have to raise 3 to? What is log base 3 of 3? What number do we have to raise 3 to get 3? That's easy. We just have to raise it to the 1. Nothing at all. We don't have to raise it to anything other than what's already there, so just something to the 1 is what it starts off as. What about 9? Well, what number do we have to raise 3 to get 9? We have to square it, so we have to raise it to the 2. We can keep going in this pattern. What number do we have to raise 3 to get 27? We have to raise it to the 3. What number do we have to raise 3 to get 81? We have to raise it to the 4, and we could keep going if we want. What if we went the other direction? Well, 2, we don't know what number we'd have to raise 3 to. But 1, yeah, we do know what number we have to raise 3 to. 3 to the what equals 1? Just like everything else, 3 to the 0 equals 1. So 3 to the 0 equals 1. We can go 1/3. What number do we have to raise 3 to get 1/3? -1. What number do we have to raise 3 to get 1/9? -2, and it would get lower and lower and lower the closer we got to 0. Once again, we'll never actually be able to get to 0 because there's no number that we could raise 3 to get 0, but we can get really, really close to 0. So at this point, we're ready to actually try plotting it. So notice our x values go pretty widely. So let's look at x values going from -10 up to positive 100. And let's look at our y values. Our y values, our f of x values, don't really manage to change very much. So we'll look at y values only going from negative 3, now let's make it negative 5, up to positive 5. Okay, so let's start drawing that in. So start here. Here's our x-axis, y-axis. So make a scale. Scale for the x will be in chunks of 10 because we have to cover a lot of ground. So negative 10, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. And we could keep going if we want, but that's good enough for us. So here is a 10, here is 100, and we'll mark 50 in the middle. 1, 2, 3, 4, 5, 50. And negative 10. So we can see the scale on it here. For our verticals, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Here's negative 1, negative 5, positive 1, positive 5. Great. Now we're ready to plot down some points. We see at 3, we're at 1, so we're very close here. We're just even less, a little under 1/3 of the way out to the 10. So let's say it's about here. At 9, so just a little bit before the 10, we're at 2. At 27, so 10, 20, 30, so a little bit before that, about a little under 1/3 of the way towards the other side. So 27, we're at 3. 81, so 100, 90, 80, just a hair in front of 80, we managed to be at 4. There we go. Now, we want to go the other way as well. At 1/3, so we are at 1, we are at 0. So we're really, really close to that y-axis already. At 1/3, so now we're getting pretty darn close. We're at negative 1. At 1/9, we're practically on top of it, but we'll never actually be on top of it. We'll just get really, really close. And we can see that this pattern is going to continue. 1/27, negative 3, 181 divided by 81, negative 4. So as it gets really close to the 0, it's going to just shoot down really quickly. So draw this side in. So it approaches this asymptotically. It gets really, really close, but it will never actually touch it. The part where it looks like it's touching it, just my human error fault, but it's not going to ever quite touch it on a perfect graph. It might look like it because of the thickness of the lines, but it will never actually do it. And as it grows more and more, it slows down because it has to go even farther out to be able to get any growth. So it slows down the farther out it gets. And we've graphed log base 3 of x. Cool. Finally, what are the domains of these functions? F of x equals log base 7, negative x plus 2. Remember, the idea we had was log base a of stuff. Then this stuff here must always be positive. So it must be positive. Otherwise, it just doesn't work. Right? If we try to take the log of 0, doesn't work. We tried to take the log of a negative number, doesn't work. So you always have to take the log of positive numbers, whatever the base is. For any base, this is going to be the case. So it doesn't matter if it's base 7 or base 50 billion. It's going to be the case that we have to have whatever's inside of the logarithm, whatever the logarithm is operating upon, has to be greater than 0, has to be a positive number. So we know the thing that log is operating on here is negative x plus 2. So we know that negative x plus 2 must be positive. It must be greater than 0. We move the x over. We have 2 has to be greater than x. So x has to be less than 2, and it can go all the way down to negative infinity because the only restriction we have is 2 is greater than x, which we could write out as anywhere from negative infinity up until positive 2, but not including the positive 2, which we show with a parenthesis to show not inclusive. Over here, g of t equals 5t times log base pi, 3t plus 7. Once again, the base doesn't really matter. It has to be positive no matter what the base is. For any arbitrary base a, it has to be positive on what the logarithm is operating on. We look at the 5t part, we might get worried, oh, is the 5t going to interact with it? 5t times log pi, 5t is really in its own world. It's doing its own thing. 5 times t, we can do that for any number. We can multiply 5 times any number, so its domain is anything at all. It's not going to actually get in our way. Once again, the only thing we're worried about is when is the logarithm going to try to take the log of a negative or 0 number. So that must, to avoid that, we have to have that 3t plus 7 must be greater than 0. Otherwise, we'll be taking a log of something that we cannot take logs of. That would break our function. So 3t plus 7 is greater than 0. Subtract by 7. 3t is greater than negative 7. Divide by 3. T must be greater than negative 7/3. So t starts at negative 7/3, but not actually is able to include negative 7/3. So it starts just above negative 7/3 and can go anywhere larger, so it can go all the way out to positive infinity. So we've got negative 7/3 shown with a parenthesis because we can't actually include negative 7/3. We can just get arbitrarily close to it, going all the way out to positive infinity. And there are 2 domains. All right, cool. We'll talk a bunch more about logarithms in the next one, where we'll explore the properties of logarithms, and then we'll see even more about how the 2 connect. We've got a lot of really interesting ideas. It's new stuff, but once you start practicing it, as you do it a bunch of times, logarithms will really start to click in. You'll get this idea of what am I trying to raise this number to get the thing I'm taking the logarithm? What does this base have to be raised to get the number that I'm taking the log of? All right, we'll see you at educator.com later. Bye.